What's up, everyone? Today we're going to learn about electrochemical cells, or batteries, basically. Here's one right here. And so we'll start with a brief lesson and history on how batteries work. So watch this TED Ed video first on how batteries work.
You probably know the feeling. Your phone utters its final plaintive bleep and cuts out in the middle of your call. In that moment, you may feel more like throwing your battery across the room than singing its praises. But batteries are a triumph of science. They allow smartphones and other technologies to exist without anchoring us to an infernal tangle of power cables. Yet even the best batteries will diminish daily, slowly losing capacity until they finally die. So why does this happen? And how do our batteries even store so much charge in the first place? It all started in the 1780s with two Italian scientists, Luigi Galvani and Alessandro Volta, and a frog. Legend has it that as Galvani was studying a frog's leg, he brushed a metal instrument up against one of its nerves, making the leg muscles jerk. Galvani called this animal electricity, believing that a type of electricity was stored in the very stuff of life. But Volta disagreed, arguing that it was the metal itself that made the leg twitch. The debate was eventually settled with Volta's groundbreaking experiment. He tested his idea with a stack of alternating layers of zinc and copper, separated by paper or cloth soaked in a saltwater solution. What happened in Volta's cell is something chemists now call oxidation and reduction. The zinc oxidizes, which means it loses electrons, which are in turn gained by the ions in the water in a process called reduction, producing hydrogen gas. Volta would have been shocked to learn that last bit. He thought the reaction was happening in the copper, rather than the solution. Nonetheless, we honor Volta's discovery today by naming our standard unit of electric potential the volt. This oxidation-reduction cycle creates a flow of electrons between two substances, and if you hook a light bulb or vacuum cleaner up between the two, you'll give it power. Since the 1700s, scientists have improved on Volta's design. They've replaced the chemical solution with dry cells filled with chemical paste, but the principle is the same. A metal oxidizes, sending electrons to do some work before they are regained by a substance being reduced. But any battery has a finite supply of metal, and once most of it has oxidized, the battery dies. So rechargeable batteries give us a temporary solution to this problem by making the oxidation-reduction process reversible. Electrons can flow back in the opposite direction with the application of electricity. Plugging in a charger draws the electricity from a wall outlet that drives the reaction to regenerate the metal, making more electrons available for oxidation the next time you need them. But even rechargeable batteries don't last forever. Over time, the repetition of this process causes imperfections and irregularities in the metal's surface that prevent it from oxidizing properly. The electrons are no longer available to flow through a circuit, and the battery dies. Some everyday rechargeable batteries will die after only hundreds of discharge-recharge cycles, while newer advanced batteries can survive and function for thousands. Batteries of the future may be light, thin sheets that operate on the principles of quantum physics and last for hundreds of thousands of charge cycles. But until scientists find a way to take advantage of motion to recharge your cell battery, like cars do, or fit solar panels somewhere on your device, plugging your charger into the wall, rather than expending one battery to charge another, is your best bet to forestall that fatal bleep.
Next, you're going to watch another video. This one will explain how galvanic cells work in more detail. These are electrochemical cells that we'll be talking about in more detail. And so make sure you pay attention to this video.
A useful galvanic cell can be constructed by using zinc and copper. The anode is a zinc bar placed into a zinc sulfate solution. And the cathode is a copper bar placed into a copper 2 sulfate solution. The two solutions are connected by a porous sodium chloride salt bridge that prevents the two solutions from mixing but allows ions to migrate. Attaching a cell shows that electrons flow from zinc to copper. Because zinc is a more active metal than copper, it is more likely to lose electrons. For this reason, the zinc bar is oxidized, producing a zinc ion and 2 electrons per zinc atom. The copper ions in solution gain 2 electrons and are reduced to copper metal. As the reaction continues, excess positive zinc ions build up in the zinc solution. At the same time, the loss of copper ions from the copper sulfate solution creates an excess of negative sulfate ions. Positive sodium ions migrate into the copper sulfate solution from the salt bridge, while negative chloride ions migrate from the salt bridge to the zinc solution and maintain neutrality of the solutions. The reaction stops when the zinc bar or copper ions are depleted. The overall cell reaction can be written like this.
All right, so just to review what you just saw in that video, on the left side here we have an anode, which is where oxidation occurs. On the right side we have a cathode, where reduction occurs. And so you basically have a metal which is dipped in its own solution, and you have another metal on the other side dipped in its own solution as well. And where oxidation occurs is, remember, oxidation is loss of electrons. So where did those electrons go? As the zinc becomes zinc ion here, it's going to send over electrons to the other the compartment, or the cathode. And so here we can attach a wire, and we can use those electrons to power something up. Okay, so you could actually light up a light bulb, for example. So on the other side, what's going on is the ion is becoming the metal. So you're actually forming more of this copper metal here. And eventually this battery will run until you run out of the zinc metal on the left, or you run out of the copper solution here on the right. Okay. We need a salt bridge to basically balance the charges, and yeah, that allows the anions and cations to move between electrode compartments. Okay. So, yeah, we'll be talking about these batteries in the next couple days. So just to summarize, there are two kinds of electrochemical cells. One is the voltaic or galvanic cell, which we just saw in the previous slide. This one uses spontaneous redox reactions to generate electricity. You can think of your cell phone battery as an example, the Duracell batteries, right? They do it on their own. They can generate power. However, electrolytic cells, on the other hand, they need electrical energy in order to create redox reactions. So think about your portable charger, for example, right? It needs energy. It needs to be charged in order to generate redox reactions. Okay? And that's pretty much it for this lesson.